All right, welcome to part number 2 of material testing. So on the screen right now, you see two examples of test samples, commonly referred to as dog bones. You can see they kind of look like a dog bone, but you'll notice that both ends are much bigger, and then in the middle there's a region that has been machined down to a smaller diameter. So here's that region in this case, this picture. We have a diagram of one here. This has threads on the end, but still you see that we have this smaller machined region in the middle, and that's where we're going to be paying attention to as we perform the test. Here's just a blueprint of one. You can see that it has some dimensions, but as we take our dog bone, what we're going to do is we're going to put it into our tester. So here we can see the two different jaws. So this one's going to be clamped in at the top and bottom, and then this will be stretched out. This one has threads on it, similar situation. The threads are on the top and bottom, and we're going to be pulling down to create our test sample or break our test sample. So as that happens, we're going to be creating a curve here. And this is the response or the reaction. As I apply a load, I'm going to expect that I have a corresponding change in length. So this P is for load. Delta L stands for change in length or deformation. So if we think about it, what's going to happen is I'm going to apply a load, and I should expect that I'm going to get some degree of stretch from that load. So as I apply a load, as I apply a load, as I apply a load, I'm going to get to a point where once I apply a load past this, it's not going to return to its original size. So this point right here, this is that point in the video where you remember that the test sample actually broke in two. So this is what's called a load versus displacement curve for a test sample. So here's an example, here's a practical example. So we have that load versus displacement curve here, but we have two different sizes of test samples. So test sample A here, it says they're both made out of red brass. Test sample A has a diameter of 0.125 inches, which is 1/8 of an inch. Test sample B has a diameter of 0.375 inches. So if both of them are tested to failure, will the applied tension force and the elongation be the same for both tests? Well, likely not, because what we will see is that this smaller test sample, it's going to take less force to break it. The bigger test sample, I should expect that it's going to take more force to break it. The problem is that it's going to create two different graphs. So I'm going to have a load versus displacement curve for this one. I'm going to have a load versus displacement curve for this one. But if they're both the same type of material, what I'm looking for is I'm looking for a curve that's going to be consistent between those two. So, as we said, the load elongation results are dependent on the sample size, so smaller versus bigger. But it says, how can test data be manipulated to represent a material and not an individual test sample? So remember that first curve was called a load versus displacement curve. What we're going to do is we're going to replace those two values. The first one we're going to replace is our load. We're going to replace that with a term called stress. And so stress, it is a load per unit area. So this now still takes into account the load, but how much area is supporting that load. So stress, the equation for stress, it says divide the load P by the original test sample cross-sectional area. So we have stress equals load over area, or P over A0. A0 means the original cross-sectional area. So that is our value for stress. The other one that we can change is going to be our change in length. And so, oops, sorry, I'm going to get ahead of myself. So it says calculate the stress in the dog bone with a 430-pound applied force. So here's our dog bone. So we know that stress is load over area. I have my area. I have to remember that this is not area, this is my diameter. So area equals pi r squared. So area equals 0.0625 inches, which is my radius, times pi. So I have an area of 0.0123 inches squared. I know that I have 430 pounds that's being applied. That's right here. I know that I have an area of my test sample of this. Therefore, the stress in my test sample is 35,000 PSI, pounds per square inch. What I would see is that if I have a bigger test sample, say for example that 0.375 test sample, I should expect that my load is going to be correspondingly larger, that I would get this same stress out of it. So the other term, I'm going to get back to this, the other term that we're going to be replacing is my change in length. So what we're going to do is we're going to introduce a new term, which is called strain. And strain, here in blue, it says, is the amount of stretch under load per unit length. So here in red, strain, amount of stretch, divided by original length. You're going to see, now here's my example. It says calculate the strain in the dog bone with an elongation of 0.0625 inches. So my original test sample is going to be this smaller region here. We know it as a length of 1 inch. So when I'm calculating my strain, amount of stretch, that is going to be my 0.0625 inches. My original length is not going to be 3 because I should not expect that this region or this region is going to be deforming. I'm going to expect that the majority of my strain is going to be taking place in this smaller region. So I have 0.0625 divided by 1 inch. I should expect that I have a strain of 0.0625 or 6.25%. Please notice that the units on strain are either inches per inch or it's represented in a percentage, where this is 0.0625 or 6.25%. Our next video, we're going to start talking about how our stress and strain curve can be deciphered and what the different regions are within that.